Good evening, and in today's video I will discuss about the mapping function of the cache memory. Basically, the different blocks in the main memory map to the cache memory whenever there is a requirement by the processor, and, and what are the different mapping function is used in the cache memory. That will be the basic discussion for today's video lecture. So before starting about the mapping functions, let's have a look at the cache memory. Typically, cache is a memory, or you can say the faster memory, which is placed between the main memory and the processor. And processor is operating at a higher clock speed, and it is very fast, whereas the main memory is relatively operating at a low clock speed. So, in order to minimize the processing capability, or to minimize the gap between the processing speed between the main memory and processor, a high-speed memory build a high-speed memory is placed between the main memory and a processor so that the overall data transmission or execution can be enhanced. There are so many different benefits we are using getting through cache memory. The details of the cache memory, other than this mapping function, we will be discussing in another video lecture. So in today's class, we will only focus on the mapping function used in the cache memory. So mapping function determine how memory blocks are placed in the cache. Main memory is a memory with a higher capacity and basically is a typically DRAM. Whereas cache memory is comparatively low capacity in comparison to main memory, typically built by static RAM. There are a number of blocks exist in the main memory, and the blocks there also exist a different number of blocks in the cache memory, and these blocks of the main memory and block size of the cache memory are same, and each block consisting of number of words, also sometimes referred as uh, word address or a block offset address. And there are three different type of mapping function. One is called direct mapping, one is called set associate mapping, and one is called associate mapping. So let's start from the direct mapping. Typically, if we discuss from this given diagram, the main memory consisting of so many blocks. So here number of blocks in the main memory is 4096. Starting address is block address is 0, and the last order of block address is 4095. So total number of blocks in the main memory is 4096. And the cache in this given example consisting of 128 blocks, and the block size of the both memory are same. That means whatever the number of size of the block in the main memory is same as that of the size of the block in the cache. So in order to differentiate between these two blocks, typically sometimes we refer block frame for cache, or we are calling it as lines in case of cache memory is concerned. And the block consisting of different words, and these words are typically required by the instruction when instruction execution takes place. And there may be number of words in a particular block, and how many words that exist, that information is basically provided. The mapping function maps a particular block, so typically particular block to corresponding block in the cache memory. And in the direct mapping, the approach is like that: the block 0 of the main memory will map to the block 0 of the cache memory, and subsequently the block 1 will map to the block 1 of the cache memory, and block 127 of the main memory will map to block 127 of the cache memory, and block 128 will map to the block 0, and so on. So the mapping which support this type of mapping, the blocks from the main memory to blocks frame of the cache, is known as direct mapping. So typically we may write that the suppose if the block number is provided, then we can able to determine in which block it will be available in the cache. And the function we are using to determine is we can express that in term of let's say bj is the block in the cache, and this is the bi, this is the block of the main memory. We are using the mod function, mod, and it is the let's say it is n, and this n is the number of blocks and the cache. So if I consider this typical example, my value of n is here, it is equal to 128 number of block in the cache. So provided the any block address of the main memory, let's say it is 50. So the corresponding block position in the cache memory can be 50 mod 128, which will give me the result as 50. That means the 50th block of the main memory will be mapped, or will be placed in the 50th block frame or block position in the cache memory. So this is the mapping function we are using for the direct mapping. And if you look at the addressing system used by the memory, in main memory we are using the address, main memory address, which is divided into basically two parts. It is one is called your block address, and one is called block offset, or you can say quad address. This is the addressing scheme we are using for main memory, and the corresponding addressing scheme we are using for cache memory, where the cache will be consisting of one is called tag bit, one is called block number, one is called word. So we may represent them as in terms of tag, block, and word, whereas their same address is number of bit to represent the main memory address, and number of bit represent the cache memory address are same, but the difference is the block size of the main memory relatively higher in comparison to the block size of the cache memory. Now coming to one numerical. So let's start how to determine in direct mapping how the mapping function works, and what are the information to extract the value for tag, block, and word. Let's start with an example. So when you have to resolve or you have to solve the numericals related to cache mapping, for a better understanding you have to draw and we have to put all the information provided in the question. So if I'll to look at this question, a cache consisting of 128 blocks. So this is my cache memory. This is my cache memory, and number of blocks it include is 128. That means my starting block is 0. This is my first block. This way my last block address will be 127. Then the main memory contain 2k block. So this is my main memory. So this is the main memory. This is the my starting block address B0, and this is the second block address, and the last block is numbered as 2k, means k value is here 1024, 2k is 2048. So starting address is 0, so it is 2047. So the main memory content 2048 blocks, whereas cache memory content 128 blocks. This is the information so far I have extracted, and each block consisting of 32 words. That means the block of the main memory as well as the block frame of the cache memory both contain what? Number of words is 32. So if it is my first of the block at word address starting with the 0 and followed by 1, then it will contain 31 word address. This is given. Then it is asking for what? How many bits are there in each tag, block, and word field in case of a direct mapping. That means ultimately it is asking for what is the tag size in terms of bit is concerned, and then that is the block size in terms of big. It is asking for what? This is the addressing format in case of cache is concerned. Okay. So how to know? So in the parallelly, I have to do the memory addressing. So memory addressing, memory is divided into block as well as word. So what is the number of blocks? 2048. So in order to find the 2048, the number of bit required is how much? It is 2048 log 2048 to the base 2. So this will be how much? This will be 2k blocks. K means 10. This will be 11. 11. So 11 bit will represent or required to represent the number 2048. And how many bit is required to represent total number word is 32? Log 32 to the base 2, which will be 5. So my total main memory address will be 11 plus 5, that will be 16 bit. So my total memory address will be 16 bit, and that will be same for the cache memory address lines also. But in case of cache, the address is divided into three parts. Here it is divided into two parts. Here it will be divided to three parts: tag, block, and word. The number of word and number of word in the cache are same. So number of bit required to represent the word also same. So it will be 5. Then the block. Block means what? Number of blocks in the cache. So how many blocks are there? 128. Starting address is 0 and 127. So how many bit is required to read 127 or to represent 128? It will be 7 bit. 2 to the 7 is 128. And what is the total memory address? 16 bit. And these two are already 7 plus 5 is 12. So the number of tag bit will be 16 minus 12, which will be how much? 4. That means 4 bit. 16 minus 12. That will be 4. So finally I can compute the tag bit is 4, block number of block bit is 7, and a word or block offset in the is 5. So this way I came to know that my cache address will be represented through tag bit 4, block size 7, and word size 5. Now come to another example. So this is another example. I have to also draw the diagram. First, let me to draw the cache memory information. What is given? This is my cache memory, and this will be my main memory. Okay. So here main memory information is 4 GB. So my main memory or the information is how much it is? 4 GB. Okay. It is byte addressable. So by default, if the addressing mechanism information is not given, we have to assume that it is byte addressable, and it is also mentioned as byte addressable. That means each byte has one address, and the size of the block is 32 byte. So 32 byte. This is my 32 byte. 32 byte. 32 byte means what? 0 0 word, 1 word, 31. Okay. Then cache size is 512 KB. This is my cache memory. Size is represented how much? 512 KB. Also, the block size is same: 0, 1, 31. And if the block size is suppose it is 32 byte and cache size is 512 kilobyte, then I can determine what number of block in cache. So number of block will be how much? 512 kilobyte by Size of the block is 32 byte. So now convert this to in binary form in power of 2. 512 means it is 2 to the power 9, k means 10. So ultimately it is 2 to the 19. This was a byte. By 32 byte means 2 to the 5. And it will be 2 to the 19 minus 5, it will be 2 to the 14. So block address. So finally catch will be represented through what? It will be represented through my tag, then block, then word. So what the information I have get so far? I have got the word size is 32 means the number of bit required to read is 5. Block size is already computed, its total number of block is how much? 2 to the 14 number of blocks. But the bit required to represent is 14. Okay. And what is tag size? I have to compute the tag size. So before that I have to determine the main memory address structure, which is represented through block plus word. So word information already given. So it is 5. And number of blocks is how much? It is 4 GB total capacity. And the size of the block is 32 bits. So total number of blocks in the main memory will be 4 GB by 32 byte. 4 means 2 to the 2 and G means billion. It's 10 to the 30. So it is 32 to the 32 byte by 32 byte means 2 to the 5. So this will give me 2 to the 27. That means 2 to the 27 is my block address and 5 bit is my word address. So it will be 27 plus 5, 32 bit address line. That means my memory, main memory is 32 bit. So 32 bit will be also the address for the cache memory. And so far I have computed the total address line is block is 14 plus 5 is 19. So remaining is my tag bit. So 32 minus 19. 32 minus 19 is how much? 32 minus 19. It will be 21. This is 13. 1 3. So my number of tag line will be 13. So ultimately the number of tag bit will be 13. Then the block size in the cache is 14 and the word size is 5. So this is the this way I can able to determine the number of address line used for cache memory. And then now look some other numericals. These all are related to direct mapping numericals. So here main memory size is how much? 128 KB. Cache size is 16 KB and block size is 256 byte. It is asking for TBW, tag bit, block bit and word bit. Also here we are asking for a tag directory size, which is nothing but the tag bit into number of lines. Line means number of blocks in the cache. Okay. So how to compute it, the tag bit? Already if you look at this, the block size is how much? 256 byte means how much? 2 to the 8. So number of block will be sorry, this is not the block number of block. This is my cache size. This is my block size. So if you divide 16 KB by 256, they will give me the number of block. So what is the value? 16 means how much? 2 to the 4 and K means 10. So 2 to the 14 by 256 means how much? 2 to the 8. So it will give me 14 minus 8 means 2 to the 6. So ultimately 6 bit will represent or required for block. Clear? Or you can say number of block is 2 to the 6 means 64 blocks is there. So you can have to draw the image or diagram, so it will be easy for you to practice. I'm doing it directly. So the number of bit for the block will be 6, and the word size, block size 256 byte, so it is 2 to the 8. So number of word line will be how much? 8 bit, and block bit will be 6 bit, and the total is how much? This is 6 plus 8, 14. And what the tag bit? Tag bit is nothing but how much you have to compute it. 128 kb means how much? 2 to the 7 plus 10, 17. 17, 2 to the 17. 17 plus what is that? 8 means 25. Address line required for the main memory is how much? 25. So ultimately, if you mark here, this main memory block size will equivalent to the combination of tag and the block, because word is common for both cache memory as well as what is that, main memory. So this is how much? This is 2 to the 17. 10 kg 10, and 7 is 17, and so far block here is 6. So 17 minus 6 will be my tag bit. How much it is? 17 minus 6 will be 11. So you have to check. I am doing quickly. It might be sometime some numerical error might be there. Oh, you have to verify it. That's the logic. So 11 plus 6 plus 8. 11, 6, 17, 23. I don't know. You have to check it. Okay. So next is tag directory. So tag bit is how much? 11 into block, number of blocks in cache, that is number of lines. How much number of lines are there? To the 6 block means 64. So my tag directory size will be 11 into 64 bit. Okay. And we sometimes ask about the comparator, means how many comparison is required to determine. In case of direct mapping, we are directly computing. That means if the block address is given by the main of the main memory, then by using the mod function, mod means what? Number of blocks in the cache. In this typical example, the number of blocks is 64. By that 64 mod, we can able to determine in the corresponding what? Block in the cache memory. So it requires only one comparator in case of direct mapping. That is the major advantage of the using the direct mapping. In the same way, the remaining question can be solved. So I am skipping it. It is for you to practice. Or if required, I am randomly can solve any question. Remaining you can practice. So let's come to this last question. What the information is given? 24-bit address space means what? The main memory size is 24-bit. That is B plus W is 24-bit. And the size of the block size is how much? 8. So block size 8 means word addressing or block offset will be 2 to the 3. So it will be 3 bit. Then cache is how much? 64 kb. So number of blocks will be how much? 64 kb by 8. So block size is how much? 64 kb is how much? 2 to the 16. So it will be 2 to the 16 by block size is 8, 2 to the 3. Ultimately, this will give me 2 to the 13. So number of blocks in the cache is 13. And what is the tag bit? So number of address spaces in main memory is 24. So that means all these three tag block and word will be 24. This is 13 plus 3, 16. So 24 minus 16, what will be the value? 8. So number of tag bit will be 8. So if I can able to know the tag bit is 8, then the tag directory size will be tag bit 8 into block, number of block in cache. How many? Number of blocks is 2 to the 13. 2 to the 13 is how much? 10 means k. It means 8k, 8k, this much of bit. So this way you can able to do the remaining question what is given here. I think you can able to do it. Now coming to the next part, that is called associative mapping, or sometimes we refer it as fully associative mapping. And one thing I want to say that the major limitation in case of direct mapping is that if you look at this given example, the block 128 and block 0 are both are coming and staying at this block of the cache. That means if a particular time the CPU needs block one of the word from the block 0, and it brings back that block 0 to block 0 position of the cache, but later another block from the 128 is required, then even if the remaining 127 position is laying vacant, it have to replace it because both are mapping to same address. So the limitation in case of direct mapping is that even if cache is empty or there may exist more block, but still we have to replace one block because the another block is mapping to this particular block in the cache. So that is the major limitation in case of direct mapping. Otherwise, the major benefit is that it is very easy to determine which block of the main memory will be available or will be placed in which particular block frame of the cache memory. So now coming to the next type of mapping, that is called our set associative mapping. So set associative mapping overcomes the limitation of direct mapping. In this approach, the any block in the main memory can be available anywhere in the cache. Means block 0 can be available block 0 position, can be available in block 1 position, can be available in block 2, can be available in block 3, can be placed in block 127, can be block available 126, like that. That means one to many mapping function. Block 0 can be mapped anywhere in the cache. Any block from the main memory can be mapped to anywhere in the where in the cache memory. And this type of mapping is, sorry, this is set associative mapping. What I am explaining is associative mapping or fully associative mapping. That means any block from the main memory can be mapped to anywhere in the cache. But one major limitation, one first advantage is that it overcomes the limitation of the direct mapping. That means if particular block 10 block 0 is available here, and block 128 which was previously mapping to same location, it can be mapped to anywhere other than the occupied one. So that is the advantage of what associative mapping. But the major limitation in this case is that in previous case we have to searching directly that location, because if I have to know particular block 50, I have to use 50 mod number of lines in the cache. Then it will identify a particular block address in the cache. Then it is easy for to find that particular block. But in case of associative mapping, you have to search from the entire cache. That means I have to search for a particular block in the main memory, in which position it is available. I have to search first block, second block, till I have to get back that block, or till I have to search the entire cache. So it is a limitation, and it will lead to aggravate, or it will lead to increase the response searching time if the number of block is more. If it is 127, I have to search 127. If the block contain 128, 256, I have to search for a particular block by looking at the 256 location. So that is the limitation of what associative mapping. Main memory is divided into block and word offset. Block offset, that is word address, and your cache is divided into tag and word. But that means ultimately the tag address of the cache is same or equal to as that of the block address of the main memory. So that is the only difference between the associate mapping addressing mechanism and direct mapping as addressing mechanism. So here cache memory address is divided to two parts: tag bits and word bit, whereas block address remain intact or remain same. Then we have to come to the what? Next one is associative mapping. So in associative mapping, what we are using, it combines the features from both direct mapping as well as from the fully associative mapping. That means like direct mapping, before no, we have to let to know the this is the number of blocks in the main memory, and this is the number of block in the cache memory. Each block in the cache is divided to number of sets. So it may be that depend upon the how many blocks in a set. Let assume that in this given example, 2 block form a set. So this is my set 0. So like that, this is my set 1, and last 2 will be my set. What is that? Set 63. Total number of set is 64. Number of block is 128. 2 block per set. So total number set is 64. Starting set is 0 and plus set is 63. Here the particular block will be mapped to, like direct mapping, it will map to the set. So I can use the same mapping function used by the direct mapping. Well, I have to replace that value of n as a block address with the set address. So here, if the same example is concerned, so I have to map the corresponding bj mod, I can say here k. What is k? K is the number of set in the block. Then I will find the location in which set it will available. That means block 0 will map to set 0, block 1 will map to set 1, block 2 will be mapped to set 2, and so on. But when it map to set 0, block 0, it can be available in anywhere in the set. At this given example, number of set is 2, so block 0 can be available in the first block of the set 0 or can be available in the second block of the set 0. So it is easy to determine because the mapping is directly mapped from block to set, and within the set it is associative or it is fully associative. But the number of block in a set will vary, and typically it will be 2, 4, 8, 16 like that. Its number. This is also referred as uh, what is that? It is referred as associativity. Means it we can say k-way associativity. Means if the k is the number of blocks in a set, then that is called k-way. And typically the value of k will be vary starting from 1, 2, 3, 4. Typically it is in form of 2, 4, 8, 6. And the size divided in the cache memory is divided into tags, set and word, and the block size and also word offset size are same for main memory. So here we have to compute the tag bit, we have to compute the set, we have to compute the word. The word's address of the main memory as well as cache memory are same. Means the number of bit represent to word is same, but there is a tag and set. This tag is something different than the tag of the direct mapping as well as the tag of the associative mapping. And we have to compute the set looking at the how many blocks are there in a cache and how many blocks are there in a particular set. Then we can able to determine the dividing the number of blocks to the number of set per block will give me or give us the value for set. So this is the set associative mapping. And the most common or most important property about set associative mapping is that in today's all the processor they support all the cache memory we are using in our PC are typically set associative mapping. That means it combines the best feature of direct mapping as well as the features of fully associative mapping. Now let's start with some numericals. Uh, this is which numericals. Okay. So start with the first numerical. The computer has 256 kilobyte 4-way set associative write back data cache. Okay, so that means the size of the cache is how much? 256 KB. This is my cache memory. This is my main memory. Block size is 32 byte. 32 byte. Same as that of your what? Main memory. Processor sends 30-bit address to the cache controller. That means the address line is used 32-bit. So 32-bit address line. Whatever the information I am getting, I just putting it here. Each tag directory entry contains additional to address tag to valid bit, unmodified bit, replacement number of bits in the address. So it is ultimately asking me what is the number of tag field in the address, or let me to compute the cache memory address in form of what? Tag, set, and what? Okay. So 4-way means what? Number of blocks in a set. So this is 1, 2, 3, 4. So this will be my set 0. How many blocks are there? Total capacity is 256. Size of the block size is 32. Number of blocks I have to determine. So number of blocks is how much? Total block size, cache memory size is 256 KB. 256 means 2 to the 8 is 256. K means 10. 2 to the 18 by block size is 2 to the 5. So total number of block is 2 to the 13. Clear? Number of block is how much? 2 to the 13 number of block. And each block is how many? 4 block. Set is 4 block. Total block is 2 to the 13. Per set there is 4 block. So number of set is how much? 2 to the 13 by 2 to the 2 means 4. So it is 2 to the 11. So number of set will be 11. What is byte addressable? 32 means 5. And total is 32 bit. So 11 plus 5 16. So it will be 16. Is it clear? So this way I can able to determine the number of tags, set and word. Like that, you can look at the second question also. Second question is what? 64 blocks, 1 MB cache, 64 blocks. Cache size is how much? 1 MB. Block size is how much? 64 blocks. So total block in the cache is how much? 64 block. So 1 MB by 64 will give me what block size? 1 MB means how much? 2 to the 20. Number of blocks is 64 by 2 to the 8. Sorry, 2 to the 2 to the 5 is 30. 2 to the 6. So it will give me 2 to the 20 minus 6, 14. Okay, let's draw it. Draw it. Okay. So I have to draw the information first. For this is for second question. 1 MB cache. This is my cache memory. This is 1 MB. 64 blocks. This is block 0. This is block 63. 4-way means 0, 1, 2, 3. 1, 2, 3. 4 means what? This is my set 0. How many blocks? 64 blocks. So last 4 will be my set 15. So 16 total number set is 16. Number of blocks is 64. 32 byte address space, 32, 36 byte address space. So your total address line is 36. So it will be divided among the three part. One is your what? Tag. Second will be set, and third will be word. Set is almost 16. 2 to the 4. 4 bit. Total this one is 36 bit. Word size is how much? I have to compute it. How to compute? If I divide the size of the cache with the number of block, it will give me this block size. So your block size is, I represent as BS, block size is cache size 1 MB 2 to the 20 by number of block 64 means 2 to the 6. So it will be 2 to the 14. 14 means how much? So it will give me the 14. Number of words in a block is 14, means 2 to the 14. 14 plus 4, 18. So 36 minus 18 will be my tag bit. Clear? So this way you can able to determine the remaining questions, question number 3 and question number 4. So it is for your practice. If you have any doubt, you can ask me later. Now coming to few more additional numericals. Now here same question what we have done for your direct mapping, but here we have modified it a little bit for set associative mapping. Now we have to put it 128 main memory. Cache size is 16 KB. Block size is much. Okay. We have to first determine what block size 256 byte means what. So this will be word address 2 to the 8. This will 8 bit. Then number of blocks in cache is how much? 16 KB by this much. 16 KB is how much? 2 to the 4 and this is 10. Okay. So block size is how much? Number of block. Number of block. Size of the cache is how much? 16 KB by block size is 256 byte. It will be 2 to the 14 by 2 to the 8 is equal to 2 to the 6. This is the number of blocks, means 64 blocks. 64 blocks. And how many blocks per set? 2 blocks per set. So how many set? Set will be number of blocks 64 by 2 way, means 32. 32 log 32 is 5. So my number of set will be 5. Set bit required to set is 5. Bit required for word is 8. So 8 plus 5 is equal to 13. Then what is the tag size? Tag size means what? This is how many byte? 128 KB. 128 KB is how much? 128 KB means how much? 128 means say 2 to the 17. 2 to the 17 by block size is how much? 2 to the 8. So number of blocks is in the memory is how much? 2 to the 17 minus 8. It will be 2 to the 9. 2 to the 9 number of blocks means 512 number of blocks in cache memory. So 9 bit is required to block plus word size is how much? 8. 9 plus 8 is how much? How much it is? 128 KB means memory to 128 KB. 128 KB means how much? K stands for 10, 9. 19, sorry, it is 19. 17. 120 means 10 plus 7, 17. Then block size is 8. 2 to the 8. 17 minus 8 is 2 to the 9. This means what? 512 number of block. So it is 9 bit. Plus your block size is 8. 9 plus 8 is equal to 17. So the main memory address is 17. So this is 8 plus 5, 13. So 17 minus 13 will be a tag. It will be 4. 4. So if it is 4, then the tag directory size with the number of tag bit 4 into number of lines in the cache. How many number of lines? 64. So 4 into 64 bit. Clear? So this way you can able to determine the corresponding information for tag, block and set. So this remaining question you have to practice. If you have any doubt, you can ask me. Now coming to few more numericals from set associative cache. This is taken from the textbook. Block set associative cache consists of 64 blocks. Cache is 64 blocks. This is cache 0, 63. 4 blocks per set. 0, 1, 2, 3. So this is set 0. And the last 64 means what? 64 by 4 is 16. So set 15. 0 to 15. So number of set is how much? Set is 16. 16 means bit required is how much? 4. Then main memory is 4096 blocks. This is my main memory. This is my cache memory. 4096 means what? This is my 4095 and this is my 0 block. Okay. And each consists of 128 words. 128 words. So what is the address line? B plus W. How many block size? 4096. 4096 is how much? 2 to the 10 is K. 11 is 2K. 12 is 4K. So it is 2 to the 12 number of block plus block offset is how much? This is 2 to the 7. So total is 2 to the 19. So 19 bit address line is used by the main memory. And it is divided among how many? S tag plus set plus word. Word is how much? 7. And this 12 is divided among set and tag. Tag is how much? Set is 4. So 12 minus 4 is 8. So it will be 847. So this way you can able to do it. Now coming to another question. A computer system has main memory 1 million, main memory 16-bit words. So I have draw the file for main memory. This is the main memory. How many words? 1 million. 1 million words. 1 million words. Okay. It has a 4K cache. So cache size is 4K. This is my cache memory. 4K. 4K word. Okay. And it is 4 blocks per set. That means number of 1, 2, 3, 4. This is my set 0 consisting of 4 blocks. And the size of the block is 64 words. 64 words. So my main memory is how much? Block plus word. How many blocks? 1 million means 2 to the 20. words and size of the word is 64 to the 6. So 2 to the 14 number of blocks. So this is 14 and this is 6. This is 20. That means my memory content 20 address. 20 address lines. Then cache is divided into what? Tag plus set plus word. Set is how much? What is the number of block? 4k by 64. 4k is how much? 2 to the 2. K means 10. 2 to the power 12 by 2 to the 6. So this is equal to 2 to the 6 block. This is 2 to the 6 blocks means what? 64 blocks where in the cache memory. And 4 blocks per set means how many set? Set is how much? 16 sets. So number of bit required is 4. This is 6. 6 plus 4 10. Tag bit will be 10. So 10 4 6. But if we were assuming byte addressable, then we have to increase because it is represented as what? 16 bit words. Here I compute only considering the word addressing. But if it is byte addressing, then this one will increase by 1. This will be 21. And some necessary changes will be tag bit will be 11. Like that. You have to compute it. Now coming to another question. Consider the memory system in which block size in cache and memory are equal. Obviously, cache size is 512 blocks, 0, and this is 512, 511. Cache memory. Main memory 8192, 0, 8191. 4 way means 1, 2, 3, 4. Set 0 and 512. So how many sets are there? 512 blocks. Set per block per set is 4. So 512 by 4. It is the number of set. How much it is? It is 2 to the 9 by 2 to the 2 is equal to 2 to the 7. Means 128 set. How much bit is required to read it? 7 bit. So ultimately my address in form of tag, set and word will be, this will be 7. Set I determine. Then what is the remaining? Here I have to find memory address. This is in form of what? B plus W. Block size is given or not? Okay. So here block size is not given, but this block is combination of tag and set. So how much it will be? B will be number of block is given. Yes, number of block is given. What is that? 8192. 8192 is how much? This is 2 to the power 10 is k, 1k, 11 2k, 12 4k. It is 3, 2 to the 13. That means number of block is 13, which will be a combination of tag and set. So if it is 7, it will be 6. Clear? So tag bit will be 6, set bit will be 6, and W is not required here because it is asking for what? Tag bit. So this we can able to compute. And now coming to another question. Let me to draw this one first. This is my main memory. This is my cache memory. Cache holds 64 KB, 64 kilobyte. 4 bytes, block size is 4 byte. 4 byte. The number of blocks is how much? 64 KB by 4. This will be 2 to the power 64 KB by 4 byte. It will be equal to 616 by 4. 2 to the 16 minus 2. 4 means 2 to the 2. So 2 to the 14 number of blocks. This is the blocks. And 4 where? Then number of set is how much? 2 to the 14 by 4. So it will be 2 to the 12. So my set will be 12 bit. And my W will be 4 byte, means 2 to the 2. 2. This is the information I have got. And what will be my tag size? Okay, I have to check it what the tag size. Main memory contains 16 million byte. 16 million byte, block size is 4 byte. So number of block is how much? 16 million means 2 to the 4, m means 20. 2 to the 24 by 2 to the 2. 2 to the 22 blocks. And this is your S plus W in case of cache. 12, so it will be 10. Clear? This is the addressing. What question is asking, the hexadecimal memory address is mapped to which cache? So I have to determine this address first. This is the answer for the addressing scheme used for what? Addressing scheme used for cache usually 10, 12, 2. This is the structure. Okay. Next is what the next information is asking. It is asking for a particular block address will map to which memory address, particular memory address. So memory address means what? This is a word address. So it is in hexadecimal form. So I have to draw it first. A, how many A? 1, 2, 3, 6. A, 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 A. The binary equivalent of this one is 1010, 1010, 1010, 3, 10104, 10105, 10106. And word size is how much? 2. So I have to, this is my word size. And this will be my block size. Clear? This way I represent. So this is my block information, or you can say block address. And this is my block offset address or word address. Okay. Then this corresponding decimal equivalent number I have to compute it. So if I have to compute it, let me to compute it. And whatever the number you will get, then what number you will get? Let's binary to decimal. The number is 1010 is 5 times. 1010, 1010, 3 times. 1010, 104 times 10 10 5 times, then it is 10 only for sixth one. So the number I am getting here is binary decimal equivalent number is uh, 279 279 279 6202 6202. This is my block address into the Western block address. So then this block address I have to map to set. Just like that, if you remembered, the corresponding block will be mapped to the set, then it will lies in a particular set in that set. How many set? How many set are there? 2 to the power 12 sets are there. So I have to use the mod function for this number into 2 to the 12 is how much? This is 1024 into 1024 2048 4095. So I have to use this mod 4095 mod 4095 or 4096. So let me to check it what the number is. 2796202 by 4096 is equal to 682 minus 682 this much into 4096. 682. Okay. So ultimately, you may have to check it. I might be wrong somewhere. It may be during conversation. So this is the process. That means what? Whatever the number I am getting, this is the block number. Then I have to apply the number of set because I have to compute that set. And once I get that particular set, because my set will be 4096. So any set I have to get from the 4096. Then once I get to that set, then it can be placed how many ways? It is 16 ways. 16 ways. Okay. You have to check it. I don't know whether it is I have done it correctly or not. That means within that set, it may be available in any of the blocks out of the 16 blocks available. So this way you can able to determine any particular address in any format, whether it is decimal, binary or octal or any address. This is the mechanism. That means you have to determine the address, you have to encode the address in form of blocks and the word address. Then you have to, if once I get the block address in any number system, then I have to map if it is direct, if it is this is set associative mapping. I have to map to the corresponding set by doing the mod function of the set number. Once I get the reminder, means mod values, then that will give me that particular blocks in the cache memory. So these are the different numericals, and these are the different mechanism we have discussed for what uh, memory mapping. And let me to conclude here. Uh, there are different three mapping things are there, like your direct mapping and associative mapping and set associative mapping. Direct mapping gives better result because it is mapping is easy. Once you get the block address, then it is easy to compute the corresponding block frame in the cache memory. But it has certain limitation for which it is nowadays not that much of use, or you can say some CPU they support it. Associative mapping in other part overcome some of the limitation associated with the direct mapping. It any block in the main memory can be placed anywhere in the cache, but the searching time will be more. So these two are combined together with the name of set associative mapping, where few sets are in consider in the cache consisting of number of blocks which determine the number of ways, or that is ways associativity, and is once you get the block number, then you have to get that mod function for to determine the particular set. Once you determine the set, then within that set the number of blocks are used. We have to sort that particular, or we have to place that particular block of the main memory. So set associative cache are nowadays used by almost all the processors, and it is more popular in comparison to direct and associate mapping. So we have done some numericals based upon the direct mapping and associate mapping. Address line used here is, it is called tag, block, and word. And the associate mapping we just address as tag and word. And set associate uses the address as in form of tag, set, and word. So this is the information about the different mapping, and remaining on cache memory will be discussed in other videos.